We begin. Empirical formula. Empirical just means determined through experimentation. So what you would find in the lab. And then formula obviously is for either an element, if it's polyatomic, or covalent or ionic compounds. So right now we're talking about compounds. Okay, so there's, I'm gonna take those separately. I'm gonna start with ionic first and then do covalent second. I just wanna remind you that an ionic compound has, when we give a formula, the formula doesn't represent one unit. It just is the ratio of cations to anions within a large unit. So I could have 300 sodiums and 300 chlorides make up one little tiny crystal of sodium chloride, but I'm not going to write that. For the ratio, I say it's 1:1. So for ionic things, when we come up with the empirical formula, that is the formula that represents the ionic compound. Okay, so here we have a first problem. When 4.11 grams of elemental 10. So elemental just means 10, the element. And then we ask ourselves, how does 10 exist? Most elements are monatomic. So we have 4.11 grams of just 10. It's reacted with oxygen, and then it makes a product. So the product that we're going to have is going to be 10 and oxygen stuck together. We know that 10 forms two kinds of ions. It can be 10-2, or it could be 10-4. But this is the kind of experiment that they did to figure out that those are the two ions that were possible. So this product has 10, some number of those, probably 1, to oxide, some number of those. And since oxide has a -2 charge, we expect that X will be 1, and we don't know about Y. If it's 10-2 oxide, Y will be 1. But if it's 10-4 oxide, we expect Y to be 2. So the goal of an empirical formula problem is to come up with the subscripts, the X and the Y. And we do this in the lab by taking measurements, but we can't do that this semester. Okay, so I know that the product is 5.22 grams and that it contains both the metal that doesn't disappear plus the oxygen that combined. And so if I subtract the 4.11 grams that we know are 10, what's left over is going to be grams of oxygen. This next thing I'm saying is important. So I'm going to do that subtracting. 5.22 minus 4.11 is 1.11 grams of oxygen. If we were talking about oxygen in nature, just oxygen gas, we would write O2. But because we're talking about oxide, the oxygen has become stable by gaining electrons. We're not going to use O2 right now. We're going to think of oxygen atom independently, recognizing that it's gained 2 electrons, but electrons don't have a lot of mass. Okay, so the first thing is to figure out for each element in the compound what the mass is in grams. We've done that. And then the next step is to convert that to moles. So I'm going to look on my periodic table, and I find the molar mass for 10, 118.71 grams of 10 in every mole. And I'm going to get some moles of 10. I'm going to do that same idea for oxygen, but I'm treating oxygen as oxide. 16, not 32. Grams of oxygen atom per mole. Because I'm really imagining it being oxide. And those 2 extra electrons, they don't have much mass. So that's me thinking there. Okay, and then I'll come up with some moles of oxygen, which is really oxide. And I'm not going to do any rounding. I'm going to save the rounding until I'm ready to put a box around my answer. Okay, so I'm just looking at my numbers. And I can tell that Y is 2 because I have 0.035 and 0.070. So the oxygen is twice the 10. I can see that. I know that Y is going to be 2. But I still want you to do the process that I'm talking about right now because the answers won't always be this obvious. So the next step in the process is to take the larger number and divide by the smaller number so that we end up with a number that is 1 or more than 1. And it looks like the moles cancel, but they don't because they're moles of different things. So I'm ending up with a number that is 2.00377 moles of oxygen for every mole of 10. And now I'm trying to imagine if that were a whole number, what would the whole number be? And the answer is the number is 2. So I put 10 on the left because it's the metal and the metals form the cations, and we always state and write the metal on the left, cations on the left, and then oxygen on the right. And this is a 1 and that is a 2. That's a 2. This is a 1. But if it's 1, we don't state 1. So this must be 10 for oxide, and the Y was 2. Okay, so let's do that same idea here. Now we're going to do iron and oxygen, so we're going to make an iron oxide. We know the possibilities are we could have iron 2 or iron 3. But there are going to be some things where you don't know what the possibilities are. I'm just telling you ahead of time, you have an idea, a check for reasonableness. Does this number seem right? So you're going to do the same thing. You're going to take your iron and recognize that product is iron and oxygen. And to find the grams of oxygen, you have to subtract. So the process is the same as the previous page. There's one extra step at the end. So go ahead and do that. Yeah, so when we end up with a number that isn't a whole number, then we're going to have to multiply by 1 in some form. And that's what I'm doing right here. I'm saying what I ended up with was 1.5 to 1. If I multiply by 1 in the form of 2 over 2, then 1.5 times 2 is 3, and 1 times 2 is 2, and now I have whole number subscripts, which is what I need. So I multiplied by 1 in the form of 2 over 2 because the number ended in 0.5. If the number had ended in, so let's say a number ends in 0.5, then we're going to multiply by 2 over 2. If it ends in something that looks like a third or 2/3, multiply by 3 over 3. If it ends in something that looks like a quarter or 3/4, multiply by 4 over 4. And then if it looks like 0.2, 0.4, 0.6, or 0.8, multiply by 5 over 5. And that's as high as we'll go in general chemistry.